Okay. So, whatever we have seen for this problem, right. So, we got that for different range, say lambda is equal to this curve A to B shows that lambda is in between 39.92 and 46.76, right. Load is in between 54 and 73. So, this part is AB. So, this equation, this is linear equation, right. So, this part is drawn. Then BC is lambda is equal to 0.2 PL plus 38, we have got this one also, right. Then from here it is start that 73 megawatt to 295 megawatt total, right. So, we get this straight line, and then last one is lambda is equal to 0.36 PL minus 32.8. So, this is C2D curve, this is C2D, that is 73.4 to 728.8 lambda, right. So, this is your PL versus your lambda graph. So, this is just a 3 different straight lines have been drawn with 3 different slopes, right, and that you can easily make it. This side is the total load and this side is your lambda, right. Next, based on this example only, we will take another some different data and we will solve this one. For example, that for the example problem in example 2, the previous one, you compute the saving for the optimum scheduling of a total load of 266.66 megawatt as compared to the equal sharing of the same load between the 2 generating units. Just hold on, right, that just hold on that tabular form, right. When total load is, I mean equal share means 133.33 megawatt each, right, this one, and what will be the your what you call optimum. If you take optimum one 266.66 we have given, so if you take this is the optimal one, then in that case Pg1 is equal to 161.11 megawatt and this is 108.55 megawatt, right. So, that means for optimal operation of 266.66 megawatt from table, that means from this table only, right, from this table Pg1 is equal to 161.11 megawatt, right, and Pg2 is equal to 105.5 megawatt. So, if loads are shared equally, then both will be that it will be divided by 2. So, it will be Pg1 will be 133.33 megawatt and Pg2 is equal to 133.33 megawatt, both are equal, right. So, based now that C1, look, C1 is your what you call just because IC1 is given, to integrate that one, C1 is equal to DC1 dPg1 into dPg1. So, integrate this one, right. So, DC1 dPg1 is 0.18 Pg1 plus 41. If you integrate this, it will become 0.09 Pg1 square plus 41 Pg1 plus K1 is a constant, right. Similarly, C2 also DC2 dPg2 your dPg2, right. So, you directly substitute 0.36 Pg2 plus 32 dPg2, that is C2 will be 0.18 Pg2 square, you integrate this one plus 32 Pg2 plus K2 is another constant, this is 2 where K1 and K2 are constant. So, their ICs are given, you have to integrate them to get the C1 and C2, right. So, now if it is these two are given, now if you take the optimal one, that optimal one means the fuel cost for generating 266.66 optimally. So, we saw that Pg1 will be 161.11 and C2 will be 105.55 rupees per hour, right. So, in that characteristic of Pg1, C1 and C2 you substitute. So, it will become 0.09 into 161.11 square plus 41 into 161.11 plus K1 plus 0.18 into 105.55 square plus 32 into 105.55 plus K2, that is equal to your 14,324 plus K1 plus K2 rupees per hour. So, K and K2 constants are here, right. Now, when loads are shared equally, the fuel cost will be Pg1 also 133.33, Pg2 also 133.33. So, in that case it is 0.09 into 133.33 square plus 41 into 133.33 plus K1 plus 0.8 into 133.33 square plus 32 into 133.33 plus K2 is equal to 14,533 plus K1 plus K2 rupees per hour. This is also K1 K2 is here also K1 K2. Now, therefore, net saving for optimal your scheduling operation, right. So, from that you can make out actually this is higher, right, because if it is not optimally shared, right. So, therefore, the net saving for optimal scheduling operation. So, this is equal sharing 14,533 plus K1 plus K2 minus 14,324 plus K1 plus K2 rupees per hour, that is 200 rupees per hour. If you do not go, the K1 K2 will be cancelled. So, if you do not operate optimally, you will be loser by 209 rupees per hour. I mean, this is simple example, because if equal sharing means this much plus K1 K2 constant and optimally means this much. So, naturally one should go for optimal operation, right. So, assuming no change, no outage throughout the year, right. So, annual saving will be 8760, because in a year total number of hours 8760 into 209. So, it will be rupees 1830840, right. So, this much rupees, right. So, now this is whatever little bit we have done, all these things, that is without your what you call without losses. Now, what we will do, we will study the economic dispatch considering line losses, right. Now, we have to consider the line loss. Now, one thing, as load flow studies we have already done. So, naturally that injected power in anywhere, that loss is equal to that. Look, generation is equal to total generation, say I is equal to your what you call M, total generation is equal to total load, say PLI plus P loss. Generation is equal to load plus loss, right. That means your I is equal to 1 to M PGI minus I is equal to 1 to N PLI is equal to P loss, right. This is the thing. Now, question is that instead of, now you have n number of buses and m number of generators. So, instead of that, this equation we can write like this: I is equal to 1 to N PGI minus I is equal to 1 to N PLI is equal to P loss, right. That means, where your this thing N is greater than M. So, where generators are there, that you consider PGI. If it is not there, PGI is 0, right. So, that is why taking this one. So, this one you can write I is equal to 1 to N PGI minus PLI is equal to P loss, right. So, this is the thing. Now, net injected power we know, no, this was your generator, say for PGI only, right, and this is your load PLI, only real power we are considering. That means, net injected power, this is your PI, that is you will come your PGI minus your PLI, right. That is your net injected power PGI minus PLI. That means, this equation it can be written as that sigma I equal to 1 to N PI is equal to P loss. That means, that sum of injected power at all buses will give you the power loss. This I wanted to mean, because this thing I will use. So, sum of injected power at all the buses will give you the power loss, right. That is why this N I took instead of N greater than M, where generators are there you consider, and where generators are not there it will be 0 minus PLI, 0 minus in general 0 minus PL, right. That is why, to show you that I is equal to 110 we took this. So, same thing, same logic we will use here, that from the law of conservation of power we can write P loss is equal to I is equal to N sigma Pi, that is that your total your this thing is equal to the power loss. Just now we showed the total power injection. So, among that you have m number of generators. So, I is equal to 1 to M PGI minus I is equal to 1 to N PLI. This is equation 23, right. So, this is that means loss is actually is equal to the total injection of power, sum of the injection of power at all the bus bars, right. This is understandable to you, right. Now, Pi is equal to net injected power at bus I, just I showed, I have given the nomenclature. P loss is equal to total line losses, right. then PGI power generated by I generator, this is understandable too, and PLI is equal to load at bus I. Now, it is assumed that PLI are specified and fixed. So, we will know that load is known to you, load is always fixed, right, and fixed, but the PGI are variables, right. So, if PLI are fixed, then from equation 3 it can be seen that P loss depends on PGI. That means if load is fixed, then P loss is function of PGI, depends on PGI, right. So, that means, so bus 1 is a slack bus, right, is a slack bus, and the slack bus power P1, Pg1 is equal to P1 plus PL1 if any load is connected at slack bus. I told you that during load flow iterative process, if any load is connected to the slack bus, that you need not consider during iterative process, because it is a dummy variable, actually you need not. But once you get the load flow studies, at that time that P1, that Pg1 should be P1 plus PL1 is a dependent variable, right, and found by solving the load flow equations. Therefore, only m minus 1 of the PGI are independent variables, right. So, that means, thus for a given power system and given PLI and QLI at all buses and voltage magnitude Vi specified at buses I is equal to 1 to 3 up to m, the functional dependent of P loss may be written as. That means, if bus 1 is a slack bus, right, that means all other, if you assume you have bus total 1 to m buses, and if bus 1 is a slack bus, then loss actually is a function of Pg2, Pg3 up to Pgm, right. That means, this that means we can write that loss actually, just hold on, loss actually is a function of this your what you call Pg2, Pg3 up to Pgm, because we have seen that P loss is equal to sigma I is equal to 1 to m your Pgi minus your this thing sigma PLI I is equal to 1 to n, but if bus 1 is a slack bus, right, and your Pg1 is equal to P1 plus your PL1 if any load is there at slack bus. That means, this loss actually function of Pg2, Pg3, Pgm. Now, this loss formula in terms of this generation thing will derive at the end of this topic, because if I try to derive this P loss is a function of all these things, then whole continuation of this thing will be lost, right, because this derivation is little bit lengthy, right. So, at the end we will make it, at this time we will assume that P loss is a function of Pg2, Pg3, Pgm, accordingly we will proceed, but at the end I will give you the loss formula, right. Right now we do not need this, right. So, we will assume that, but if I try to do this, then all this continuation will be, I mean that will be disturbed actually, right. So, equation 24 depends on the load flow solution, that is true, right. So, now expression for total fuel cost is given by Ct is equal to I is equal to 1 to m Ci Pgi. This is actually 24, I have made this one actually 24 ASA, right. So, this is known total fuel cost, already earlier we have seen, right, this one. Now, subject to your, now loss is considered, because total generation is equal to load plus loss. So, that is why this equation I am writing I is equal to 1 to m Pgi minus P loss, which is function of Pg2, Pg3 up to Pgm minus PL, the total load is equal to 0, right. So, generation minus loss minus load, this is the power balance equation, right. So, this is equation 25, right. So, and Pg limit is given, Pgi mean Pgi lying in between Pgi mean and Pgi max, right. So, now what we will do, then again we will follow that same thing, that Lagrange multiplier. So, we will first consider the case without the general limits, for example, general limit, that we will see later. The augmented cost function is defined as Ct tilde is equal to I is equal to 1 to m Ci Pgi minus lambda into that in the bracket sigma I to 1 to m Pgi minus P loss function of Pg2, Pg3 up to Pgm minus PL. This is equation 27, while lambda is the Lagrange multiplier, right. If we take that derivative with respect to lambda, right, and is equal to 0. So, if you take the derivative with respect to 0, so in general this equation, this power balance equation actually it will become 0, right. That means, So, that means look, if you take derivative with respect to lambda, there will be minus sign here, but is equal to 0. So, no need to consider minus before that, is equal to 0, right. So, that is why that d ct tilde upon d lambda is equal to I is equal to 1 to m p g I, that is sum of the all the generation minus P loss. Look, P loss is a function of Pg2, Pg3, Pgm, but again and again not writing in a function of. Now, it is understandable that P loss is function of the generated power except slack bus, right, minus PL is equal to 0. This is equation 28. Now, in this equation again you take derivative with respect to Pg1, that is dC1 upon dPg1 will be your this thing, I mean take the derivative with respect to Pg1. I mean if it would do so, it will be something like this. For example, I am just writing for you just that you can understand this, right. Ct tilde actually, this Ct tilde, right, I am writing for you, Ct tilde is equal to sigma I is equal to your 1 to m Ci Pgi, right, then minus your what you call this your lambda, this lambda, it is I is equal to 1 to m. So, we can write in bracket that take Pg1 out, right, take Pg1 out, then this one you can write, then I is equal to 2 to m, then Pgi, then minus your this thing what you call minus this P loss function of all these things. So, minus your P loss, it is function of Pg2, Pg3 up to Pgm, right, then minus PL. So, this is the thing and this is your bracket close, right. So, this is your, now if you take derivative with respect to Pg1, then dct tilde, then dPg1, right, this one, for this one will be dC1 upon dPg1, right, sorry, dPg1, it will be there, right, and then here it will be again minus lambda is equal to, you said 0, because you took this is sorry, this sigma is not there, right, here sigma is taken. So, only Pg1, right. So, if you take the derivative with respect to Pg1, the lambda will be there, but this is function of Pg2 and this thing, this will be 0. This is also function of Pg2, Pg3 will be 0 and this is the load is constant. So, all this derivative will be 0. So, it will be your minus lambda into your what you call this thing dC1 upon dPg1 minus lambda is equal to 0, that means dC1 upon dPg1 is equal to lambda, right. So, that is why this your this equation when we take the derivative with respect to Pg1, dC tilde upon dPg1 is equal to dC1 dPg1 minus lambda is equal to 0. This is equation 29. Now, another thing is that means dC tilde dPgi is equal to dCi upon dPgi minus lambda when I is equal to 2 3 m, right. That means just now I your this thing, just hold on, just now I explained that now for dC1 dCt tilde dPg1 is dC1 dPg1 minus lambda. Now, next actually when you take derivative dC tilde upon dPgi for I is equal to 2 3 m, but here I is equal to 1 already derivative is taken here, when I is equal to 2 3 m at that time you take. So, at that time dC tilde upon dPg or dC tilde upon dPgi is equal to dCi upon dPgi, that is fine, then minus lambda, right, your what you call minus lambda in bracket, it will be your 1 minus delta P loss upon delta Pgi, that is equal to your this thing is equal to 0 when I is equal to 2 3 m. I mean if you take the derivative with respect to Pgi, that I, right, that means this one you are taking I is equal to 2 to m for ith one, right. So, it will be your this thing will be just your what you call this thing will be dCi upon dPgi, this one will be dCi upon dPgi and minus lambda you are taking derivative with respect to ith Pgi, right, Pg, that is Pgi, that means here it will be only 1 will be there, that is why this one is here minus this loss is a function of Pg2, Pg3 up to Pgm. So, it will be dP loss upon dPgi, that is why minus lambda in bracket 1 minus dP loss by dPgi. That means, when you are taking for I is equal to 2 to m, right. So, as you are undergraduate student mostly, right, I understand that you have understood this, right. You take the derivative of this, equation with respect to ith one, ith Pgi, when I is equal to 2 to m, that is why because of that we are taking with respect to Pgi, that is why only ith term, so only 1 will be there. So, minus lambda into 1, and this is function of Pg2, Pg3, so dP loss dPgi. So, dP loss dPgi, that is for I is equal to 2, 3 m. Hope you have understood this one, right, nothing, no difficulty actual, right. So, this is that, so 28, 29, 30, these 3 equations we got, right, from this derivative. Next is your 30 may be written as this equation 30, right. That means, this equation 30 we are writing in this form. Look, equation 30 may be written as that Li dCi dPgi is equal to lambda, right. What we are doing actually, that we define that Li into dCi dPgi is equal to lambda, where Li is equal to 1 upon 1 minus dPLS upon dPgi. That means, this equation for your understanding rewriting, this equation we can write, that your lambda is equal to dCi Pgi, then dPgi divided by 1 minus dP loss by dPgi. This one we can write, right, and we are defining that Li is equal to 1 upon 1 minus dP loss upon dPgi. This one we are defining. That means, lambda equal to Li into dCi upon your what you call dPgi, right. This is lambda. So, that is why means this equation only, right. That is why we are writing this equation, as your Li dCi is equal to dPgi, that is your what you call is equal to lambda for I is equal to 2, 3 m, right. That means, Li is equal to, this is given 1 minus dP, that is I is equal to 2, 3. Now, Li is known as penalty factor for the ith generator, right, and from this equation, if we take Li dCi Pgi is equal to lambda, that means, from equation 29, right, that is equation 29, that is your this equation, that dC1 upon dC1 dPg1 is equal to lambda, right. If you multiply, this is actually 1 into dC1 dPg1, that is your L1 into dC1 dPg1 is equal to lambda. That means, your L1 is equal to 1, right. So, but L2, L3 are not 1 because they are related with this one, right. So, but L1 is equal to 1. That means, that is why I have written here that your Li is known as penalty factor for ith generator. Also note that from equation 29, L1 is equal to 1, right. So, that means, in general, so this is your, if you include here also L1 it is given I is equal to 2, 3 m, but in this equation if we include L1 also, that is L1 is equal to 1, right. Then this necessary condition for optimization given in 29 and equation 30, it is L1 dC1 upon dPg1 is equal to L2 dC2 dPg2 up to Lm dCm dPgm, that is equal to lambda. This is equation 34, but L1 is equal to 1, right. So, equation 34 actually it indicates that for optimal scheduling operation that operate all the generators such that their product Li into dCi must be lambda for every generator. When loss term was not there, this L1 loss term was not there, L1, L2, Lm, it was not there, right, because at that time loss was not considered. But as soon as you consider the loss, L1 is 1, which okay, but L2 to Lm you have to calculate. That means you have to know that from the loss formula and the derivative, that you have to compute L2 Lm L2 up to Lm, right. So, that means what? This dC1, dPg1, dC2, dPg2, all these things, they are ICs, that is incremental cost, and they are weighted by their penalty term, penalty factor we call, right, penalty factor Li, that is L2 up to Lm, right. So, this is the condition. So, what we will do, right, what we will do, we will take one, I mean every theories whatever we will do, we will see that one example is taken, right. Actually, when you teach in the class, we exchange so many conversation with the student, right. So, here you are not in front of me, so I cannot go for conversation, right. So, anyway, but anyway, hope you are understanding all this, right. So, a large penalty factors makes the plant less attractive, that is true, and a smaller incremental cost from the plant is required, right. So, naturally then your fuel cost will be minimum. So, that is why, but a large penalty factor makes the plant less attractive, right. So, now say an example 4, this example is taken. I have taken few examples so that you can understand. There are two bus problem, bus 1, bus 2. This generator Pg1, Pg2. Our objective is to real power generation. We are not considering reactive power anything. This is bus 1. PL1 is equal to 300 megawatt and PL2 is equal to 70 megawatt. So, sample power system, right. So, this much, and incremental cost of these two generating units, right, it is given. IC1 is given 0.35 Pg1 plus 41 rupees per megawatt hour, and IC2 also same 0.35 Pg2 plus 41 rupees per megawatt. Two IC1 IC2 they are same, right, identical, right. So, this is given, and another thing is a loss expression is given, right, that a loss expression, power loss expression is given, that is your P loss is equal to 0.001 Pg2 minus 70 whole square megawatt. This expression is given. So, you have to determine the optimal scheduling and power loss of the transmission link, right. Transmission link means that this line loss, transmission link, right. So, question is that when we will solve this problem, with nonlinear equations will come, directly cannot be solved, right. So, for this example I will take some trial and error value whatever I have got, and I will give you the how to solve it, right. Later stage when we will take the different type of problem, this problem iteratively I will not give you the solution, I will give you the solution for other problem, but I will give you final equation how to do it, but this will be an exercise for you, right, and that do iteratively, right. So, I will come to that. Okay, thank you.